This is the first lesson on quadratic functions. If you think back to grade 10, in grade 10 you looked at linear functions, and that was the only function you looked at. And a linear function in general form looks like this: y equals ax plus b, or y equals mx plus b. And the a tells you something, and the b tells you something. The a tells you the slope, and the b tells you the y-intercept. That's basically what we're going to do with quadratic functions. The simplest quadratic function is y equals x squared. So I want you to have a look at that and see how it's a little bit different than just basically y equals x. And the only difference is the square, but that square changes what our function looks like. So we're going to look at two or three particular forms of a quadratic function, and one of the forms is called standard form, and it is written ax squared plus bx plus c. And what these kind of functions always look like is something called a parabola. So when you look on the picture to the right, you see a parabola. And a parabola is just a U when it's facing up, or an upside down U when it's facing down. And just like a line has certain characteristics, x-intercept, y-intercept, slope, a parabola has characteristics as well. And one of the most important things that a parabola has is the vertex. So the vertex is the tip. The vertex is the very top or very bottom of a parabola. And its coordinates, as we're going to use them, are always going to be PQ. Now, remember, the first coordinate is always your x coordinate, and the second coordinate is always your y coordinate. But P and Q are going to be the letters we use just for the parabola. So the tip, the vertex of the parabola, is either going to be a maximum, which would be a top, or a minimum, which would be a bottom. So lines go on forever, but parabolas don't. They have a top or a bottom. The axis of symmetry divides the parabola in half. So the nice thing about a parabola is it's symmetrical. If you know something about one side, you know something about the other side. So if you know one coordinate on the right-hand side of the axis of symmetry, then you can find its matching coordinate on the left-hand side. It's the equation of the axis of symmetry is x is equal to p. And remember, the coordinate of the vertex is p comma q. So this line right here, that's our axis of symmetry right there, that has the equation x is equal to whatever the value of the x coordinate is. So this is really nice, and it just gets a bit of getting used to, but you'll become very familiar with it. The x-intercepts are called the zeros of the function. And again, one of the things that we need to recognize right now, and if you look at this simple picture over here, there may be two x-intercepts, whereas a line, there usually is only one. So these are these basic ideas that we're going to look at today. We're gonna try to convince you that a parabola is a U, and it is symmetrical across a line, and it has a vertex, and that's what we're going to focus on. So before we investigate the quadratic function in, again, general or standard form, if I ever say general or standard form, I mean the same thing. Let's look at the basic one, the absolute simplest parabola, y is equal to x squared. So here's what I'd like you to do. I'd like you to have a look at these two examples, and you can do this two ways. You could use a table of values, or you could use your graphing calculator. So I'll just do the first one for you, and then I want you to pause the video and practice what I'm doing. So if we were going to make a table of values for y equals x squared, let me do this one. We'll do y equals x squared, and in this one I'll use we'll always use black for our basic. Now, when you make a table of values, I didn't give you a very big graph. We always want to choose some x values, some negative values for x, some positive values for x, and always choose 0. So I'm going to use these points, and then I'm going to substitute them in. So when I plug in a negative 2 into x squared, it's very important that you remember you're going to put negatives in bracket, and you're going to get a positive 4. And similarly, when I plug negative 1, I'm going to get a positive 1. And that's 0, and that's 1 times 1, and that's 2 times 2. So we're going to go ahead and plot these points. And we're going to talk about this much more at school. So I'm going to plot these points, and I'm going to draw, just as long as it's not straight, as long as it's not pointy, I'm going to draw a nice curvy line. So there is a table of values for y equals x squared, the basic. So then the question is, well, we're just going to change it to y equals negative x squared. And similarly, we're going to make a table of values, except here's what I'm going to do this time. I'm going to use my graphing calculator, and again at school, we're going to work on this a little bit. So the first thing we do with our graphing calculator is we enter in the y equals window, we enter x squared. And this button here beside the alpha is always your x. And I recommend you always use this button below the clear, raised to the power 2. Now you also have a square right here that would work, but if we're always using this for our exponent button, then that's going to help us. When we ever want a graph, there's a graph button right here, but we're always going to press this one first and mess around if we have to. I'll help you with this in school. So zoom 6. And here's our picture, and there's our parabola. But there's a really nice function, and it's above the graph button, and it says table. So anything in blue, we press the second button. If we go second table, here we have a ready-made table of values, and all we have to do is scroll up and down. So again, we used negative 2 right here, negative 2, and the calculator's telling me 4, negative 1 is 1, etc., etc., etc. So this is a really nice function. We don't always have to make a table of values by hand, so I really recommend you do this one. So when I use my table of values for y equals negative x squared, I just go into my y equals, and I'm going to punch in negative x to the power 2, and again, second table, and here I go here, negative 2 is negative 4, negative 1 is negative 1, etc., etc. So I'm just going to copy that table on here. Negative 2 is negative 4, and negative 1 is negative 1, 0 is 0, 1 is negative 1, and 2 is negative 4. And when we plot that, they share the vertex, but this one is a parabola that faces down. So I want you to pause the video, either by hand or with a graphing calculator. Go ahead and plot 1/2 x squared and y equals 2x squared. And what I would recommend is using a different color for each one, because it's going to be really important to see why something happens. Okay, so I'm going to do this one in green, and again, I'm just going to use the same points, some positives, some negatives, and whether you use your calculator or not, here's what you get. So when we go ahead and plot that, we have this one. We have to guess a little on this one. And 2, 2, negative 1.5, and negative 2, 2. And then we could go ahead, and if we actually wanted to, if I plugged in a 3, I get 4.5, and if I plugged in a negative 3, I get 4.5. So again, as long as you have this basic idea of what's happening. So there's our y equals 1/2 x squared, and that's what you should have got. When we plug in y equals 2x squared, again, I'll pick the same numbers. Now there's going to be a little problem here because a couple of my points go off the graph, but if we kind of are careful, so 0, 0, 1, 2, and then if I go 1, 2, 3 up here, 2, 8, negative 1, 2, and negative 2, 8. And again, I just try to draw my best curvy line, and there I have it. So in looking at all of these pictures, the only thing we did was we added a number in front of the x squared. And these are things we want to notice. When you change that number in front of x squared, what you should really recognize is something happens to the graph. And if I ask you right now to tell me, would you say something like this? So let's look at our key ideas here. When y is equal to positive x squared, this is our basic parabola. This is the one we're going to compare things against. Well, what can we say about it? Well, the only thing we can say is it opens up, because we have nothing to compare it against. But when we look at y equals negative x squared, well, what I want you to notice is, well, this one opens down. And what makes it open down? Well, the only thing we changed was a positive to a negative. So we're going to see something really clearly, I hope. When the coefficient, the number in front of x squared is positive, what I want you to see is these parabolas open up. And when the coefficient, when the number in front of x squared is negative, it opens down. And if you look at these two examples on the right, 1/2 is a positive number, 2 is a positive number, and both of those are opening up. But what happens when we put in a number other than 1? So I'm going to call that A. What happens when we plug in a number, and the number we're going to use is A? Well, what happens then? Well, hopefully, when you look at that number and that number is less than 1 but greater than 0, like the 1/2, the green picture, what happens is the graph mathematically gets squashed, it gets put down, it gets compressed. But you might look at it and say it got fatter. And basically, if you would imagine pushing down on it, it would squish out, it would get fatter. Well, what happens when A is greater than 1? Well, it gets skinnier. And really what it's doing is it stretches. It's like you're tugging on it and you're pulling the points higher and higher, and the graph gets skinnier. So it stretches vertically. So given we have a basic idea of what a parabola is, what it looks like, and a couple of the characteristics, then all of a sudden, well, what happens when you start changing things, just like in grade 10, when we change the number in front of x and we change the number after x? So remember grade 10, when you had negative 2x, well, you had a negative slope. The line went down from left to right. What happens when you had x plus 3? Well, you had a y-intercept, and your basic line moved up by 3. And those are the same ideas that we're going to see with the parabola. So let's just look at a few and just look at some of those basic characteristics, except we're changing up the parabola a little bit. So again, I'm always going to do my x squared in black, and I highly recommend you color code because it can get really confusing. So we'll always draw our x squared. There's our x squared. Let's do this one in blue. So I'm not gonna make a table of values. I'm gonna go to my calculator, and I'm gonna get my calculator to make me a table of values. X squared plus 2. And if we zoom 6 and draw and have a look at it, zoom 6, there it is right there. And you would say, wow, I hope you look at that and go, oh, my parabola went up by 2. And if we wanted to get our table of values, there's our table of values right here. -2 is 6, -1 is 3, etc. So I'm just going to go ahead and plot those. So we have -2 comma 6, -1 comma 3, 0 comma 2, 1 comma 3, and 2 comma 6. And what I would hope you would see is those parabolas are the same, just the blue one is literally slid up 2. When we look at x minus 1, again, we could get out our graphing calculator and again do this really quickly. It's one of the great things about our calculator, and just go x squared minus 1. And if you want to see what the picture looks like, look at that. It's just slid down 1. And if you wanted to see your table of values, there's my -2 comma 3, -1 comma 0, etc. So I'm going to go ahead and plot that. So here's my vertex right there. There's my -1 comma 0 and 1 comma 0. There's my 1 comma 3 and -1 comma 3. And when we draw that, what you see is that thing is shifted down. So the key idea then is our parabolas still look the same. They still look like a u, and they still look like an x squared, a basic one, but they've been slid up and down. So when y is equal to plain old x squared plus a number, what happens is we shift up, and we shift up whatever that number is. When you have y equals plain old x squared minus a number, what happens is that shifts down, and it shifts down whatever that number is. Now everything shifts down. So for example, in the red one, the parabola goes down by 1, the 1 coordinate and the 2, everything goes down exactly the same. Okay, let's have a look at what happens when you have two functions that look like this. Again, we're going to draw my simple y equals x squared. Here's our -1 comma 1, -2 comma 4, and what happens when we have it in brackets, x minus 1 squared. So we could make a table of values. We could plug in -2, -1, and 0, but I'm going to go to my graphing calculator, and I'm going to enter it, x minus 1 squared. And again, I'll zoom 6 just to have you look at the picture. And what you should see is that parabola is moved to the right. It's the same looking parabola, but it's moved to the right. And it's moved to the right 1. And we'll see that in a sec. And if we get our table of values, there's our -2 comma 9. There's our -1 comma 4. There's our etc. So I'm going to go ahead and I'm going to plot this one in blue again. And here's what we get. We get this. We get these points. And when we connect those, we get the parabola. Looks exactly the same. But again, what's happening is every coordinate is moved 1 to the right. So everything is gone 1 to the right. When we do x plus 2, again, I'm not getting out the calculator this time. I'm just going to plot it for you. Here's what we get. We get this parabola right here. So again, I've done the exact same thing, just skipping this step. And there's my parabola. So that red parabola looks just like the black one, except it's slid to the left. So again, our key ideas are we're changing what the function looks like. We're putting in some numbers and we're seeing what happens when. So the key idea right here is when we have x minus something, when we have our equation that looks like that, what that minus does is it shifts to the right. And it shifts to the right whatever number is there. What happens when we have y equals x plus a particular number, in brackets all squared? Well, what happens is it shifts to the left. And it shifts to the left whatever that number is. So our key idea today is we're still seeing u's, and all these u's have a vertex and an axis of symmetry, and sometimes they open up and sometimes they open down, and sometimes they're fat and sometimes they're skinny, and sometimes they're a little bit to the left and sometimes they're a little bit to the right. And that's what we want to mess around with. And the best thing that helps you do that is a graphing calculator, because it shows you the pictures really, really quickly. So if we for every quadratic function that looks like that, we can do a few things to it. We can put a number in front, we can put a number in the bracket, or we can put a number at the very end. And depending on what these numbers are, what happens is our parabola moves around, it stretches, it compresses, it flips upside down, it does all these things. So there are a few important ideas that help us decide what's happening. So if we look at the sign of the x squared term, sign of the number, so that's going to tell us the up down. So we're just going to treat this like there's an invisible number 1. So this tells us, is it opening up? Is it opening down? So let me write that. So here's up / down. Now, as soon as you put a number other than 1, again, this is the compress, this is the stretch. Now, if it's a -2, it's flipped upside down and stretched down. Then we have the vertex. And the vertex, again, is the top or the bottom. And the vertex, if we add a plus or minus number on the end, or if it's written more general, and this is going to be something that you're going to see a ton, then what we can find out is we can find the vertex from this. And I'm just going to write this right now, but we set it above. The vertex is going to turn out to be P comma Q. And finally, this idea of the axis of symmetry, well, the axis of symmetry is simply x is equal to the x-coordinate, P, of the vertex. But again, this axis of symmetry is really easy to find, but it's really valuable because, like I said, if you know one coordinate on one side, you know the matching coordinate on the other. So let's look at 2 quick examples that are kind of putting everything together. And what we might want to do first is think about what's happening. So first of all, in this question, in this first one, we have a leading coefficient of 1. There's an invisible 1 in front of there. So given that it's a 1, and given that it's a positive 1, it's going to open up. So again, I'm just going to do the x squared in black. Here's just our basic plain old x squared. And again, what I know, because the leading term is positive 1, I know this one is going to open up as well. But here's what I know. I know given that this is x minus in brackets, this thing is going to move to the right too. So every single coordinate on this parabola is going to go to the right too. And again, right now, I know 4 from my basic parabola, and that's what we can use to go ahead and graph this without using our calculator. And again, what the number after the x squared stuff does is it moves it up or down. And again, given that's a -3, that's going to say it's going to move down 3. So here's basically what we could do. We could look at our basic parabola, and we could just use this transformation. And the vertex is probably the most important point, so that's where I would start. So I'm going to do this one in green. So in doing this one in green, I'm going to start here. I'm going to go down 2, and I'm going to go down 3, and I'm going to go right 1. And that's going to be the vertex of my parabola. And for this coordinate right here, I'm going to go down 3, right 1. And for this coordinate down here, I'm going to go down 3, right 1. And this coordinate, I'm going to go down 3, right 2. And I'm going to go down 3, right 2. And then I'm simply going to connect those dots. And again, what we've just done is drawn a parabola without making a table of values by understanding what each part in the form of a quadratic does. At school, I'm going to touch base with you on these last two, and we're going to look at we're going to look at the calculator, we're going to look at a table of values, and we're going to see what that one does. Okay, so last one, I'm going to draw my basic parabola, 1, 1, 2, 4, and here's the idea of the matching. And I'm just going to draw this basic parabola. And then we're going to look at this, and we're going to use the same idea of points over there, and we're going to draw the parabola. So first of all, what does this number that is not 1 in front does? First of all, the negative flips it. So the negative flips it upside down, and the 2 stretches it. So it makes it thinner, stretchy, and this one right here is up 5. So if we looked at our vertex, we could imagine imagine the parabola being flipped upside down and then stretching down by 2, or stretching down by 2, and if that wouldn't move, 0 moves 0, and then we move up 5. So there's our basic idea right there. We flip this thing upside down, we stretch the coordinates by 2, and we go down. So in this one right here, if we flip this to here, and then we stretched it by a factor of 2, which would mean 2 times -1, and then we move that up 5, that's what we get right there. If we looked at this coordinate right here, that point gets flipped, then it gets multiplied by 2, so it goes to there, and then it gets moved up 5. And finally, this one, same thing right here. +4 goes down to -4. -4 stretches to -8 down here, and then we come up 3, and we get to -5, and similarly over here. So we can imagine what's happening to each point, and we will get the perfect picture. So key ideas for this introduction is what a parabola looks like, and when you start to add to the basic y = x², what do those numbers do?